Okay. Okay, today we start with the section 3.5, solution sets. Okay, in this section, we'll state the relationship between invertibility of matrices and solutions to the systems of linear equations. First, if A is an n by n matrix, which is invertible, and B is a vector in Rn, then the system Ax is equal to B has a unique solution, which is A inverse times the vector B. Okay, all you have to do is just multiply A inverse on both sides. Then you will have X left in the left-hand side, and right-hand side should be A inverse times B. So, if you have this type of linear system of equation, which can be written in the matrix form, Ax is equal to B, where A, X, and B can be given in this way. An easy way to solve this linear system of equation is to find A inverse and just multiply it to B to get the solution X, which is minus 1 and 1, 0, like this. Okay, so this can be solved with this command here. Define a matrix and vectors, and define an inverse of the matrix A, and then all you have to then you can just multiply A inverse to the vector B, and also then you will have the solution minus 1 and 1, 0. You will have a solution vector like this. Also, if you solve this linear system of equation Ax is equal to B with this command, then you will have the same solution like that. So you can solve it in this command, or you can just multiply A inverse to the B, the vector B, to get the solution that you are looking for. Okay, here, the homogeneous linear system like this. It can be written in this form, in the matrix form, like this, where A, X, and 0 vector is like this. Then the vector X is called a trivial solution in here. And this non-zero vector solution is called the non-trivial solution. Okay. Since a homogeneous linear system always has a trivial solution, we only have two cases left. One is it has only a trivial solution, or it has infinitely many solutions. So if we have any single non-trivial solution, that means we should have infinitely many solutions. Okay? For the homogeneous linear system of equation, like this. Here, a homogeneous system with m equations and n variables such that m is less than n, then it has infinite many non-trivial solutions. That's what this case says. This notice says. Okay, this theorem follows from the observation that we had. Here, since the existence of multiple solutions depend only on the coefficient matrix, and since a homogeneous system always has at least one solution, namely the trivial solution, so multiple solutions for a linear system are possible only if the corresponding homogeneous system has multiple solutions. This can be happened only if and only if when it has a non-trivial solution. So this is what it says. If for the homogeneous linear system of equation, if it has a non-trivial solution, that means it has infinite many solutions, vice versa. Yeah. Homogeneous linear system here. You have suppose we have a homogeneous linear system of equation like this, then we can check the augmented matrix, and then we can find the RREF of A. Then this is RREF of A. then this means it has four variables and three equations. So which means we have what? One free variables at least one free variables, which means it has infinite many solutions. From this REF of A, yeah, we can we know we see there is one free variables on the first. So let this x4 be an arbitrarily real number R. Then the solution can be written as this. All xi's, other xi's can be written by using this R. Okay, and also this can happen for any r's, which means r may not be 0. That means this solution is a this solution can be a non-trivial solution. So the linear system of equation has infinite many solutions. But also, yeah, if r is equal to 0, then all xi's are 0. So that's the trivial solution case. So it has a trivial solution and non-trivial solution, and which means it has infinite many solutions. Okay, this is the example. So all you have to do is just check the REF of the matrix or augmented matrix to see whether you have free variables or not. Okay, here, this is a very important concept. Given a linear system of equation AX is equal to B, then AX is equal to 0 is called the associated homogeneous system of linear equation of AX is equal to B. So if we have this non-homogeneous system of linear equation, then we consider this corresponding associated homogeneous system of it. Okay, then see the relationship between those two. Okay, suppose we have a non-homogeneous linear system of equation like this. Then associated homogeneous linear system can be written in this way. From here we clearly know. From here, we try to find the solution of this homogeneous associated homogeneous linear system. Okay, here, so let okay, here, yeah, we from this linear system of equation, we make augmented matrix from this linear system of equations like this. Then find the RREF of it. Then like that can be found in this way. So from here we know there is a free variables here and here. So x4 and x6, x4 and x5 can be can have no free variables. So let x4 is equal to r and x5 is equal to s. Then we can find other xi's using the r. So this xi's can be written in this way. Okay. So this means this is for this r and real number r and s. This forms a set of solutions for this homogeneous linear, non-homogeneous linear system of equation. But samely, we only think the homogeneous linear system of equations and its corresponding augmented matrix, and then find the RREF like this. Then from here, we can easily find the solution for the this homogeneous linear system of equation like this, which is very simple. All you have to do is just put the free variables R and S for R and S, and then write all the other xi's in terms of R and S like this. So it can be in this way. Then the important thing is here, when compared geometrically the solutions to the system and those of the associated homogeneous linear system, the solution set for the associated homogeneous linear system is merely translated by the vector x naught below like this. As you see here, this is here. This was the solution for the non-homogeneous system of equation. This set of vectors plus this non-zero vector, and here this is the solution set for the homogeneous associated homogeneous system of linear equations. And the only difference is just adding this solution to this to make the whole set of solutions for the homogeneous, non-homogeneous system of equation. What this shows a very important concept. In here, we call the vector x naught a particular solution which can be obtained by substituting R equals S equals 0. Okay. Here, what this means is this. If you have the linear system, non-homogeneous linear system of equation like this, then you can think associated homogeneous linear system of equation AX is equal to 0, like that. Finding the solution set for this homogeneous, associated homogeneous system of equation by using REF is very easy. Then all you have to do is just find a particular solution that satisfies this, which is x0. That can be any solution that satisfies this. And just add this x naught to the whole set of vectors in this solution set for this associated homogeneous system. This is what it says. The reason is this. Suppose AX is equal to 0 and AX0 is equal to vector B, then A times x plus x0 is equal to AX plus AX0, which is AX is equal to 0 for that x, and AX naught AX0 is equal to B vector, which is B. What this means is x plus x0 is a solution for this non-homogeneous system of equations, which means a system of linear equation AX is equal to B has a solutions, and W be a solution set to AX is equal to 0, and if x0 is a particular solution, any solution to AX is equal to B, then this set of vectors is always a solution set of AX is equal to B. Okay. The geometric meaning of x naught plus W, which is a solution set of AX equal to B, is a set of translation when a particular solution x0 is added to a solution set W of AX is equal to 0, as you see in here. If this is a solution set for AX is equal to 0, then x0 plus this W is a solution set for AX is equal to B. Only difference is here, this solution set W contains 0 vector. So it forms a solution space. It's a vector space. But here, this x0 plus W does not include a 0 vector. So this is not a vector space. That's the only difference. So this solution set has much better properties that we can use. Okay, theorem 3.5.3 is an invertible matrix theorem. So now we can add a couple more. Yeah, we had this, and we had this already. Now we add 0 is the unique solution to AX equals 0, and AX is equal B has a unique solution for any given vector B in Rn. Okay, so we added one more equivalent statement for this invertible matrix theorem. Here, remark. A vector of the solution space of AX is equal to 0 is orthogonal to the rows of A. Here, as you see, AX is equal to 0. Here, AX is equal to 0 can be written in this way. Okay, the first row of A time inner product of first row of A and the vector X is equal to 0, and the second row and X's inner product is 0, and the inner product of mth row of A and X is equal to 0. It can be written in this way. What this means is the AI with the inner product of AI and X is equal to 0 for all i's, which means if X is a solution to AX equal B, which means any row of A is orthogonal with the solutions of AX is equal to B with the solution vector, which means the vector in the solution space of AX equals 0 are all orthogonal to the row vectors of the matrix A. That's what it means. This is what it means. If AX is equal to 0, then this X is orthogonal to any row vectors of A. This is what this AX is equal to 0 means. Okay. Consider the system of linear equations like this. It's homogeneous system. Then you can, let's check orthogonality of the row vectors with the solution. First, from the matrix and vector B, and if X is, so we knew this 1, 1, 3, 2 is a solution vector, is a solution for this linear system of equations. So we find the inner product of V with each rows of A in this way. Then we can easily check the inner product are all zeros. So V is orthogonal to row vectors of the coefficient matrix A because 1, 1, 3, 2 satisfies all these equations as we checked earlier. Here is the hyperplane. Line of xy plane. The solution set of a linear equation and where this AI or A2 is not 0. The plane of xyz space is the solution set of a linear equation A1x plus A2y plus A3g is equal to B, where not all of AI's are 0. Okay, this is what you have learned in the earlier chapter 1. Now, we define the hyperplane of a given vector. The solution set of this linear system of equation where not all AI's are 0. Okay, then this solution set of this linear equation is called the hyperplane of a vector A1, A2, an. Okay, this is the definition. Okay, we note if B is equal to 0, then the solution set is a hyperplane passing through the origin. This hyperplane is a solution set of n times x is equal to 0 when n is equal to A1, A2, an. Okay, so as I mentioned on the blackboard, okay, this is suppose let n is equal to a vector A1, A2, an, then the solution set of n and x is equal to 0 for a non-zero vector n can be written as a n perv, n perpendicular, n perv. This can be written in this way, is called an orthogonal complement of n. And n is called a normal vector of the of this hyperplane pi, which is n perv is this. Okay, so this graph shows the for hyperplane and orthogonal complement of the vector n here, like this. Okay, I think that's the end of section 3.5. And now section 3.6, special matrix.